Hello my friends, and welcome back to the Today Machine channel.
The production process begins with the creation of models, from which molds are made. Simultaneously, the melting operation processes raw materials into high-quality molten metal. These two elements, molds and molten metal, are then combined during the pouring process. After casting, the components undergo extensive finishing in the cleaning shop, where they are ground, blasted, and meticulously measured using advanced Zeiss technology. Precision is paramount when producing such large parts, and this is where Zeiss technology plays a vital role. The foundry utilizes high-precision measuring instruments to ensure the exact dimensions of each part. The Zeiss Autos LRX 3D scanner, designed for large-scale parts, offers a large measurement field, deep penetration, and bright lighting, which are essential for the challenging working conditions. This scanner enables the digitalization of entire components, creating accurate digital twins that can be shared with customers. The foundry's commitment to innovation is reflected in their continuous improvement of manufacturing processes, focusing on precision, digitalization, and resource efficiency. Rather than aiming for ever larger parts, SimpleCam strives to enhance the accuracy and efficiency of their processes, making them more energy and resource efficient. The use of digital twins, powered by advanced measurement technology, allows SimpleCam to stay at the forefront of the industry, ensuring that each component meets the highest standards of quality and precision. GUN Weilung specializes in producing forging bodies for oilfield drilling tools. The company manufactures high-quality tools ranging from 5 inches to 42 inches. These tools are widely utilized in drill bits, stabilizers, reamers, and other oilfield equipment. The production process primarily involves free forging, which enhances the organization and performance of metals. Free forging yields higher mechanical properties than castings, offering strength improvements of 50 to 70%. This method reduces material waste and produces parts closer to the final shape, making it ideal for small batch production and flexible design changes. It is particularly effective for parts such as straight or bent shafts and rings, which benefit from the streamlined distribution of material during forging. The process also meets special quality requirements, such as improving raw material integrity through upsetting. The company's forged products are recognized globally, serving markets in over 20 countries and regions. Ecological hydrostatic tools utilize advanced technology to perform roller burnishing and deep rolling processes, enhancing surface quality and component durability. These tools rely on a hydrostatic system where pressurized fluid creates a cushion around the rollers, enabling precise and controlled application of force without direct mechanical contact. In roller burnishing, the tool uses hydrostatically supported rollers to plastically deform the surface layer of a workpiece. This process smoothens the surface by reducing micro-roughness, improving surface finish, and increasing wear resistance. The hydrostatic pressure ensures consistent results across various geometries and materials. For deep rolling, the hydrostatic tools apply controlled compressive forces to induce residual compressive stresses into the surface layer of the component. This enhances fatigue strength, reduces stress corrosion cracking, and extends the component's lifespan. The non-contact nature of hydrostatic support minimizes tool wear and enhances precision, even under demanding conditions. Forged steel crankshafts are vital components in heavy-duty engines, designed for optimal performance in industries such as automotive, marine, and industrial machinery. The manufacturing process of these crankshafts begins with the forging operation, which involves shaping the steel under high pressure. This process enhances the material's strength and durability by aligning the grain structure. In a forge rolling operation, the forged billet is progressively shaped through a series of rolling steps. This step ensures the crankshaft achieves the precise dimensions and surface quality required for its critical role. A 12,800-ton screw press is often used to exert the necessary force for the forging, followed by a 2,500-ton hydraulic trimming and calibration operation. This stage trims excess material and ensures the crankshaft is within the desired tolerances, improving its overall fit and performance. To maintain the structural integrity of the crankshaft, a controlled cooling operation is implemented. This step prevents distortion and ensures uniform hardness across the component. The cooling is carefully controlled to avoid stresses that could affect the part's reliability. After cooling, the crankshaft undergoes automated warm straightening operations. This process corrects any minor deformations that might occur during cooling, ensuring the crankshaft is perfectly straight. The entire production process is closely monitored with automated systems for consistency and precision, resulting in a high-quality, durable crankshaft that meets the demands of heavy-duty engine applications. The M30 MILLTURN is a versatile machine tool designed for the complete machining of complex shafts and chuck parts, such as crankshafts, with exceptional precision and efficiency. This multifunctional machine combines multiple technologies: turning, boring, milling, and sometimes even gear cutting or deep hole drilling, into a single integrated system. It allows for a wide range of machining operations without the need for multiple machines, significantly improving productivity and reducing cycle times. For crankshaft manufacturing, the M30 offers a swing of up to 520 mm and a machining length of up to 1,800 mm, making it suitable for parts like crankshafts with a length of 550 mm and a diameter of 150 mm. The machine is equipped with advanced features that provide high flexibility in machining operations. One of the key highlights of the machine is its ability to operate as both a lathe and a 5-axis machining center. The 5-axis capability is crucial for machining complex geometries, such as the intricate shapes found in crankshafts. This feature allows for the simultaneous movement of the workpiece and the cutting tool along multiple axes, enabling the precise machining of the crankshaft's curves, chamfers, and bearing surfaces. Additionally, the machine features 4-axis turning and 6-side machining, which allows for comprehensive processing of the crankshaft from multiple angles in a single setup. This eliminates the need for part handling and repositioning, ensuring higher accuracy and reducing the potential for errors. The in-process measuring system further enhances the precision of the machining, allowing for continuous monitoring and adjustments to ensure that the crankshaft meets the required tolerances. The machine also features a powerful coolant system with 80 bars pressure, which aids in chip removal, cooling, and maintaining the quality of the machining process. The high coolant pressure ensures that even tough materials and deep cavities in the crankshaft are effectively managed during machining, improving the surface finish and extending tool life. Moreover, the workpiece transfer system enhances productivity by enabling smooth transitions between different machining stages, reducing setup times and improving cycle times. This is especially beneficial when machining complex parts like crankshafts, which often require multiple stages of machining, such as turning, milling, and drilling. The machine's ability to combine various machining technologies in one compact system makes it an ideal choice for manufacturers looking to streamline operations, reduce costs, and achieve high precision in the production of crankshafts and similar complex parts. The production of seamless steel tubes is a highly intricate process that involves multiple stages of material preparation, melting, forming, heat treatment, and final finishing. Raw material preparation. The process begins with the preparation of raw materials, primarily scrap steel, which serves as the base material for production. Companies like Żelazniarne Podbrzeżowe, a prominent European steel manufacturer, use advanced scrap processing facilities to collect and prepare steel scrap. This includes the separation of non-ferrous metals, plastics, and other impurities. The scrap is then reduced in volume and prepared for melting in an electric arc furnace. Melting and refining. In the electric arc furnace, EAF, steel scrap is melted at extremely high temperatures, often reaching 1620 degrees Celsius. The melting process typically takes 1 hour for each batch, during which additional alloys and deoxidizers are introduced to adjust the steel's chemical composition. This refining stage ensures that the steel meets the required quality standards for the next phases of production. Once the steel is melted, it is transferred into a continuous casting machine, which molds the liquid steel into solid blocks called billets. These billets can have either a square or round cross-section, depending on the specific requirements. After cooling, the billets undergo a final inspection for quality control. Hot rolling and tube formation. The billets are then fed into a hot rolling mill, where they undergo a series of shaping processes to transform their initial solid block form into tubular shapes. The billets are first cut into shorter lengths, which are then reheated in a carousel furnace to reach the necessary rolling temperature. At this point, the billet is pierced on a piercing mill to create a hollow tube. The tube is then elongated through various stages, using a process called elongation, where it is pulled through a series of rollers and mandrels. The tube undergoes significant lengthening, up to 20 times its original size, during these steps. Further reduction and sizing. The elongated tube is then passed through a series of rolling operations, such as a stretch reducing mill, which further reduces the tube's diameter to the desired size. The final dimensions are achieved through a process of cold working, where the tube is drawn through dies or mandrels under controlled conditions. The tube's length can reach up to 90 meters at this stage. After this, the tube is cooled and cut to the required lengths, typically around 1 meter long. The tubes then undergo further inspection for dimensional accuracy, external and internal quality, and surface imperfections. Final inspection and testing. Once heat-treated, the tubes undergo thorough quality checks. This includes non-destructive testing, NDT, methods like ultrasonic testing, which is used to detect internal flaws, and visual inspection to ensure the surface quality. The tubes are also measured for dimensional accuracy, ensuring they meet precise specifications. In this stage, the tubes are often subjected to additional surface treatments, such as pickling in acid baths to remove scale, followed by coating with zinc, galvanization, to enhance corrosion resistance. Zinc is applied electrochemically in a process called galvanizing, where the tube is dipped in a bath of molten zinc or subjected to an electrolytic process that coats the surface with a protective layer. Once these final operations are complete, the tubes are bundled into packages for shipment to customers. Some tubes are further processed into special forms, such as welded pipe fittings or flanges, and some may be coated with PVC or other protective coatings. Cutting, packaging, and shipping. The finished tubes are then cut to the required lengths, which could range from a few meters to several meters, depending on customer specifications. The tubes are further processed to ensure they meet specific requirements, such as end facing, deburring, and marking for identification. A significant challenge arises when machining steel with a monodiamond tool, as the carbon atoms in steel bond with the diamond, quickly dulling its cutting edge. This limitation makes traditional diamond tools unsuitable for such applications. To overcome this, the workpiece is first pre-processed using a carbide or CBN, cubic boron nitride, tool. Following this, Mossner diamond burnishers are employed to smooth the surface effectively. This method often eliminates the need for post-polishing, saving considerable time and improving efficiency. The process begins with the selection of the highest quality raw materials, adhering to stringent standards. Advanced CNC turning and grinding machines are employed for initial machining, while automatic tool setting based on Chemo's calculations. Bevel gears are then milled using the C300, the world's largest bevel gear cutting machine, allowing for the precise production of large and complex components. The entire production follows the closed-loop process, an iterative workflow that ensures maximum precision at every stage. Modern Klingelnberg measuring systems are employed for quality control, verifying that gears meet the highest standards of accuracy and performance. Heat treatment, performed in an in-house facility with a monthly capacity of 140 tons, enhances the durability of the gears. Grinding processes accommodate bevel gears up to 1,100 millimeters in diameter, with grinding burn inspections ensuring surface integrity. Further quality checks include magnetic particle inspections for surface cracks, guaranteeing reliability and longevity. Every component undergoes meticulous final inspections and customer acceptance tests on site. The workshop not only manufactures bevel gears but also provides engineering services, such as contact pattern optimization, load calculations, and simulation of gear dynamics. This holistic approach caters to a wide range of industries, from standard applications to high-end sectors like aerospace and Formula One. The process begins with the melting of the alloy in a separate furnace. The molten metal is then transferred into a cold injection chamber, typically using a ladle or automated system. This step ensures that the die remains cooler and extends its lifespan. Once the metal is in the chamber, a hydraulic piston rapidly injects it into a steel die under high pressure, ranging from 350 to 3,500 tons depending on the machine model. The high pressure ensures that the molten metal fills every cavity of the die, creating detailed and consistent shapes. After cooling and solidifying, the die opens and the finished part is ejected. OMS Presse machines are designed for precision and efficiency, with advanced hydraulic and electronic systems ensuring optimal performance. Their programmable controls simplify operations and reduce cycle times, while their robust construction guarantees long-lasting durability. Gravity casting and sand casting are two common methods, but gravity casting stands out for its superior ecological benefits. It reduces waste, saves energy, minimizes water use, and improves air quality while enabling the use of more sustainable materials. Gravity casting involves pouring molten aluminum into preheated permanent molds using gravity. This method is ideal for manufacturing complex, precise components with excellent surface quality. In contrast, sand casting uses sand molds, often prepared manually or mechanically, which is more suited for less intricate components with lower surface quality. Gravity casting generates up to 70% less foundry waste than sand casting. For every 100 tons of aluminum alloy produced, gravity casting prevents 70 tons of waste, preserving natural resources and reducing landfill needs. Companies producing 1,000 tons of components annually can cut waste by 700 tons, delivering both environmental and economic savings. Gravity casting requires up to 50% less energy compared to sand casting, contributing significantly to lower greenhouse gas emissions. A company using 1 million kilowatt-hours annually for aluminum casting could save 500,000 kilowatt-hours by adopting gravity casting, reducing its carbon footprint and energy costs. The process produces up to 90% fewer fine dust emissions, enhancing air quality and protecting human health. This reduction is especially impactful in regions with high levels of air pollution, improving public health outcomes near foundries. Unlike sand casting, gravity casting does not require water for mold preparation, making it a vital alternative in water-scarce areas. Gravity casting is less sensitive to impurities in recycled materials, allowing a higher proportion of recycled aluminum in production. This supports a circular economy by reducing dependence on virgin raw materials and aligning with decarbonization goals. The production of large gears is a critical aspect of many heavy-duty industrial applications, particularly in sectors such as steel manufacturing, shipbuilding, mining, and power generation. These gears, often fabricated from high-quality steel or ductile iron, are essential for driving and transmitting large amounts of mechanical power in systems like mills, crushers, and rotary kilns. P. van der Weggen Gears BV, a leader in this field, produces gears up to an impressive 16,500 mm in diameter and weighing up to 250 tons per piece. The company combines state-of-the-art technology with advanced CNC machining to deliver both large and small gears with precision and quality. Fabricated girth gears, often used in applications such as cement mills and mining equipment, are made from steel with a maximum hardness of HB 350. These gears are produced using a unique welding process that ensures the maintenance of critical material properties such as hardness and tensile strength, which are essential for the demanding environments they operate in. The high-quality welds and carefully controlled fabrication process ensure the integrity and performance of the final product, even under extreme loads and stresses. Additionally, this method allows for shortened lead times, which is particularly valuable for projects with tight deadlines, without compromising the precision of the gear's performance. In some cases, gears are cast from high-quality steel or ductile iron, depending on the specific application requirements. Casted gears in steel are also hardened to a maximum of HB 350, ensuring they are durable and resistant to wear and fatigue in heavy-duty applications. Gears made from steel alloys obtained from renowned casting shops provide excellent performance and longevity, especially when they are subject to high impact or continuous use. Ductile iron gears, on the other hand, can reach a maximum hardness of HB 360 and are often made from materials like quality GGG70. These materials offer excellent toughness, which is essential for gears that are subjected to shock loading or varying operational conditions. One of the most significant benefits of fabricated and casted gears is the ability to produce large gears with extremely high precision. With advanced CNC technology, manufacturers can ensure that each gear meets the strict tolerances required for optimal function. This technology allows for the production of gears with exceptional surface finishes and minimal variation in critical dimensions. Whether they are being used in large-scale industrial machinery or smaller, precision-driven gearboxes, the ability to maintain tight tolerances is key to the longevity and efficiency of the equipment. These machines are designed for heavy-duty operations such as machining large and complex workpieces, including turbine rotors and crankshafts. The HCW machines offer exceptional precision, with a high level of power and accuracy, making them suitable for industries requiring heavy and dimensionally precise components. They are equipped with expansive travel ranges on the X, Y, and Z axes, which allows them to accommodate oversized workpieces. Additionally, the design of the HCW series allows for the creation of specialized workstations, tailored to the specific needs of clients for advanced and precise machining operations. The Škoda FCW series, on the other hand, provides a lighter, more compact solution without compromising on performance. This series incorporates modern spindle slide designs, which allow for precise and dynamic movements. The X, Y, and Z axes are guided by compact rolling bearings, ensuring high precision and smooth motion. An innovative feature of the FCW machines is the automatic compensation for any deflection in the spindle slide during operation, which ensures that the machine maintains its accuracy even during extensive machining cycles. The machines also offer a high level of automation, with options for automatic tool changes, process measurements, and monitoring of tool life, which can significantly increase efficiency in high-volume production. The Škoda SR series of universal horizontal lathes is designed for efficient and precise machining of rotational workpieces. These machines are ideal for applications such as machining turbine rotors and crankshafts. With NC controls and a modular design, the SR series offers great flexibility, allowing for a wide range of configurations and the addition of accessories such as milling, grinding, and boring tools. This versatility makes the SR series suitable for complex operations that require high precision and diverse machining capabilities. An example of Škoda's advanced capabilities is the HCW 3200, which boasts a 103 kilowatts main drive, a spindle speed of 3,000 revolutions per minute, and a quill extension of 2,000 millimeters in the Z-axis. The installation of a new Mach engine involves a highly specialized and intricate process to ensure its performance and reliability in marine applications. This begins with the complete disassembly of the engine shortly after its factory acceptance test. Each component is carefully packed and prepared for transport, ensuring that all parts remain intact and secure during transit. The disassembled engine is then transported to the shipyard, where the critical installation phase begins. The engine block is precisely positioned and secured on board the vessel, forming the foundation for reassembly. Expert technicians meticulously reassemble the engine, adhering to stringent quality standards to guarantee its operational integrity. Once the reassembly is complete, the engine undergoes a series of functional checks and tests. These steps culminate in the engine's successful startup, demonstrating its readiness for service. The Mach, known for its efficiency and reliability, is a robust choice for marine propulsion, exemplifying engineering excellence at every stage of its placement process. Phase 1. Bladeless rotor balancing. The initial phase focused on the 49-ton bladeless rotor. Correction planes were adjusted in a 2+2 configuration to address unbalance effectively. Phase 2. Partial blade fitting. In this stage, partial blades were installed across 4+4 stages, increasing the rotor mass to 51 tons. With expanded correction planes, 2+21, precise balancing was achieved. Phase 3. Fully fitted blades. The rotor's final configuration featured complete blades, 6+6 stages, bringing its mass to 54 tons. Unbalanced correction was executed using a limited 1+1 plane system. Rehabilitation process. The shaft underwent extensive rehabilitation steps, starting with preheating to mitigate stress during repair welding. Following welding, the shaft was subjected to coarse lathe machining, fine machining, and grinding. A thorough dimension check ensured compliance with exacting standards before finalizing the shaft reconstruction. This overhaul highlights advanced balancing techniques and precision machining, ensuring enhanced efficiency and reliability of the LP rotor, a critical component in steam turbine operations. The process begins with selecting high-quality 45 steel, which meets the chemical and mechanical requirements of standards like GB 699 and GB 307. The steel should have Mo content below 0.1% and pass a hot upsetting test. Precision cutting ensures proper material sizing for subsequent steps. Due to the deep decarburization layer in domestic raw materials, peeling is essential to remove this layer and enhance the surface quality of the crankshaft. The blanks are heated in a stepwise gas furnace to a forging temperature of 1180 degrees Celsius. Uniform heating ensures optimal plasticity and prevents internal defects. The forging process includes pre-forging and finish forging. Pre-forging ensures even metal distribution, aiding the filling of the finish forging die and reducing die wear. Finish forging achieves the crankshaft's near final shape. After forging, excess material is trimmed off using a press. This step defines the rough dimensions and edges of the crankshaft. The crankshaft undergoes twisting on specialized equipment at 950 degrees Celsius to 1050 degrees Celsius. Twisting ensures correct alignment and geometry by applying calculated torsion forces. Calibration is conducted twice using a hydraulic calibration machine. The first correction ensures straightness of the main shaft and proper angular alignment between rod and crankshaft diameters. After rotating the crankshaft by 90 degrees, a second correction is performed at a temperature above 800 degrees Celsius, typically 850 degrees Celsius. Normalizing and tempering the crankshaft refines the microstructure, improving mechanical properties and ensuring a hardness of HB 180 to 228 with a grain size of level 5 to 8. Post-heat treatment, the crankshaft undergoes temperature suspension control, stress relief, and shot peening to improve fatigue strength. Flaw detection ensures there are no surface or internal defects. Anti-rust treatment is applied, followed by rigorous inspections to ensure quality compliance.